Are you tired of this happening to you? Do you want to save your numbers from being integraled? Then get yourself the arithmetic derivative for only pi dollars per month. It's going to work wonders.
Papa Flammy's Advent Calendar.
Good morning, fellow mathematicians. Welcome back to another video. You might have already seen it in the introduction. I hope you did like this little skit. I've tried my best to make it quite funny, as always. We are going to talk about something really special today you might never have heard of before, called the arithmetic derivative. I'm terribly sorry. So you might know of the regular differentiation, but when you differentiate constants, you are going to end up with zero. This is not the case for arithmetic derivatives. It underlies two little rules, but smart people have expanded this to even real numbers and rational numbers and stuff like this. It's really quite cool. And this arithmetic derivative might not have too many uses. People introduced it to prove stuff about prime number conjectures, but never mind, it's just fun to do. So arithmetic differentiation underlies two little rules, namely that if we have p being prime, then well, p differentiated is just 1. So you see, our arithmetic derivative at the moment is just going to apply to numbers greater or equal to 2. And the second rule it underlies is what you might call the, well, product rule for differentiation. P times q prime is nothing but p prime times q plus q prime times p. And well, these are the only two rules we can make use of. But why not advance this idea to the number 1 also, so that our p can also be 1? 1 is not a prime number, so none of those rules really apply to it at the moment, but we can make clever use of this right here. We are working with natural numbers or integers at the moment, so rules of addition and multiplication and stuff do work on them. So what's the arithmetic derivative of 1? Well, you see 1 is nothing but 1 times 1, so this always holds. But with this, we can make use of the product rule right here. So we get 1 differentiated times 1 plus 1 differentiated times 1. But this is nothing but 2 times, well, the arithmetic derivative of 1. So we have this conclusion right here, that some element is equal to 2 times the same element. But this can only hold if the arithmetic derivative of 1 is just 0. So that immediately implies, that's equivalent to saying that, no, it immediately implies that the arithmetic derivative of 1 is nothing but 0. So we have already advanced our number system right here, for which this arithmetic derivative holds, using simple logic and operations on natural numbers. Okay, so we have shown the arithmetic derivative for one element, but there are so many elements in the natural numbers. So why not try this arithmetic derivative out for some certain example? Let me think about 69 would be really funny. Or let's be even funnier, let's choose the best prime number ever, 57, Daddy Croton Dick, Fields medalist, number 57. So what's 57 differentiated? Well, how does this make sense right here? How can you even differentiate a number like this? Right now it's not a prime number, so what could we do? Well, if you think a bit further, we can, well, decompose every number into its prime factorization uniquely. So 57 is nothing but, 3 times 19. That's the prime factorization. Really cool prime number, right? Really cool. And at this point we can, well, just make use of the product rule right here. So we are going to end up with 3 differentiated times 19 plus 19 differentiated times 3. Well, those are prime numbers, so those differentiated are just 1. So we end up with 19 plus 3, which is 22. And we could go further. Maybe you could write a program which spits you out the arithmetic derivative of a number, and then it's going to take a next iteration, calculating the arithmetic derivative of this number, and so on until it reaches 1, for example. and does 0 in the end, because the arithmetic derivative of 1 is 0. So you could go on, so 22 would be 2 times 11, so this makes 13 as the arithmetic derivative, but that's a prime number, so this differentiated is just 1 and then 0. So after 4 iterations, that's 4, this is 2 squared, 2 times 2, it's going to go to 0 in the end. So that's one example, but what about the number 8, for example? So 8 differentiated. What is 8 exactly? Well, this is 2 to the third power differentiated. We could write it out 2 times 2 times 2 and then differentiate it using the product rule right here. But this is quite a mess. And for this purpose, I would like to introduce the power rule now. And I would like to prove it for random arbitrary natural number powers. So as you might have noticed, I've written out a little proposition, and whenever Papa's writing out his Nazi propositions right here, then, well, we are going to make use of the mathematical induction principle of mathematical induction. So you see, we want to show that for all n out of natural numbers, where the natural numbers this time are without 0, it holds that, well, this rule is true, our power rule. Please note that if p to the nth power is already the unique prime factorization, meaning p is a prime number, then this p prime is just going to be 1. So the special case, when our 8, for example, is already factored in 2 to the third power, this is just n times p to the n minus 1th power. With that out of the way, let's get started. Also our p, we want it to be greater or equal to 1, because we don't know what the arithmetic derivative of 0 is. We are just going to go by the simple rules we have established a few minutes ago. So what's our base step then? Well, p of 1 in this case. So p of 1, what's that exactly? Well, this is p to the first power but prime. So this is just p prime. But we can rewrite this because this is nothing but 1 times p prime times p to the 0th power, where 0 is nothing but 1 minus 1. So our base step already holds, and now we are going to assume that our proposition is true for some random arbitrary but fixed k out of natural numbers. Assume p of k, but what is that? Well, p to the kth power differentiated nothing but k times p prime times p to the k minus 1th power is true. We are just going to assume this. And now we want to see if this proposition ensures our statement to be true for the successor of k, k plus 1. So what happens to p of suck of k, which is nothing but p of k plus 1? Well, just write out the left-hand side at first. So we have p to the k plus 1th power differentiated, but p to the k plus 1th power is nothing but, well, p times p to the kth power prime. And now we can make use of our simple rule we have established in the beginning, namely the product rule. So this makes p prime times p to the kth power plus p times p to the kth power but prime. And it wouldn't be induction if we wouldn't use our induction hypothesis. So let's make use of the hypothesis at this part right here. So let's plug this in right here. So we are going to end up with, well, p prime times p to the kth power plus p times k times p prime times p to the k minus 1th power. And you see, p times p to the k minus 1th power is going to evaluate to p to the kth power in this case. So we have p prime p to the kth power plus k times p prime p to the kth power. And you see it works out like a charm, because we can just factor out p prime times p to the kth power on both terms to factor out a k plus 1. So this is nothing but k plus 1 times p prime times p to the kth power, but p to the kth power is nothing but p to the k plus 1 minus 1th power. So we want to bring it into a state where it's obvious that we have used the principle of mathematical induction, because this statement right here has ensured our statement to be true for the k plus 1th member of natural numbers. And now we have successfully established this rule right here. And now we can just make use of this to solve our problem we have left behind a few minutes ago, namely what the derivative of 8 is. Well, this is nothing but 2 to the 3rd power, but prime, meaning we are going to track down the 3. Then we are going to take the derivative of 2, but like I said, this is going to evaluate to 1, it's a special case. And also we are going to reduce the power of 2 by 1, so 2 squared. So overall, our arithmetic derivative of 8 is going to be, well, 12. And the cool thing is, now our arithmetic derivative is greater than our original number. What the question would be, is there a certain number where the arithmetic derivative is going to grow infinitely large over time? So, are there numbers which aren't going to 0? Maybe that's an open conjecture, I really don't know. Maybe that's the new type of Collard's conjecture. I hope you did enjoy this video. If you did, please like and subscribe and recommend the channel if you like. Also, there's something called arithmetic differential equations, and that's really quite cool, but that goes way over my head. It's just way too complicated for me. I don't get anything at all when reading into this topic. Never mind, if you want to hear something about it, I can read into it and maybe I can make sense of it. Don't forget to activate the bell button. Don't forget to share those videos I create. And up until the next video, have a flammable day, I guess. I love you guys. Appreciate you. Ciao.
Bast dich gerade, der will den ganzen Korb lassen.